Today, we're stalling. The Cessna is capable of flying at high airspeeds, diving down towards the Earth at almost 170 knots. Learning to ride the edges of the envelope is fun, fundamental, and can be life-saving. The recovery from a stall is an important, non-standard maneuver that all pilots must master. So let's go and try it out.
Welcome back to Navigraph Academy and to your journey towards attaining your very own virtual private pilot's license. Today's plan is first to explore stalls and why they happen. For example, why does lift suddenly decrease when we hit a specific low airspeed? And how does the plane react in this early stage of the stall, a phase which we call the incipient stall? Then we'll look at the situation that develops if the airspeed continues to decrease. And this leads us into the fully developed stall discussion. Lastly, we'll try diving to maximum speed. And flying this fast makes the control surfaces full of aerodynamic energy. And in this state, it is very easy to overstress or overspeed the aircraft structure, propeller, or the engine. And we'll teach you how to avoid all of this, all while enjoying the high-speed fun. First, let's look at stalls. Do you remember the balance of forces that we covered in our previous lessons? You may recall that an aircraft in level flight has a perfect balance between lift and weight. And we also talked about lift being a product of both airspeed and of angle of attack. Increasing our pitch attitude will increase our lift, and so will increasing our airspeed. Remembering these facts, we can consider what happens when we reduce our airspeed. As airspeed begins to trail off, we will start losing lifting ability. However, naturally, weight is unchanged, so with less lifting force available to counter the force of gravity, we'll start descending. If we are to maintain level flight at a lower speed, we will again have to regain the lost lifting force. This is done by raising our pitch attitude, thus increasing our angle of attack. As angle of attack increases, the airflow over the wings is angled further and further downwards, causing an equal and opposite reaction that creates a larger lifting force. Thus, as we reduce our airspeed, we must raise our nose in order to maintain level flight. However, there is a physical limitation to how much we can angle our wings. The airflow consists of air molecules flowing across the wings, much like water flows across the backside of a spoon held under a tap. Considering the spoon for a moment, if we increase the angle of the spoon further and further, we'll see that the water is redirected further and further away from the original vertical direction. This is exactly the same physical phenomenon as when airflow is redirected as a result of increasing the angle of attack of our wings. But as we increase the spoon's angle to the water, we find that suddenly the water breaks contact with the spoon, and the stream of water returns to its original flow direction. The water stream has now separated from the spoon, causing a rapid loss of water redirection. The airflow over the wing experiences the same thing. When we reach a critical angle of attack, the air molecules streaming across the wing will begin to separate from the wing surface. Remember, the downwards redirection of airflow was the primary cause of our lifting force. So as we reach the critical angle of attack, the downwards redirection of airflow begins to reduce, and we will experience a marked loss of lift as a result. Here is a diagram that presents the lift as a product of the angle of attack. We can see that the lift increases steadily to about 13 degrees angle of attack, and at this point, the wing profile experiences the maximum amount of lift. Any further increase in the angle of attack will first start to reduce the lift, and then at the end of the curve, the wing profile will completely lose all lifting capability. Operating between these angles of attacks, we are in the incipient stall. In the incipient stall condition, the wing is still generating lift, but any further increase in angle of attack will decrease the total lift generation. That means that any further increase in pitch will increase our descent rate.
Let's take a look at how the incipient stall presents itself in the aircraft. Here we are in level flight. First, we make sure we're at a relatively high altitude. This ensures safety if the stall develops into a spin. For incipient stalls, at least 5,000 feet off the ground is a good safety margin. We most often practice stalls at idle power. This time, we're doing a straight stall, meaning we'll maintain our course and our wings level throughout the maneuver. As I prepare to lower our speed, remember to look straight ahead, finding a landmark. Let's slowly retard our throttle to idle. Left rudder is required to maintain coordinated flight due to the reducing slipstream effect. Our airspeed will slowly start to come back. As I keep raising our nose to prevent any loss of altitude, I add some trim to assist. We can see that we're approaching the no-flap stall speed, or the so-called clean configuration stalling speed. It is marked by the bottom edge of the green band on the airspeed indicator. As we get close to the stall, we're going to start to hear a stall warning whistle.
Stall.
This warning activates approximately 5 to 10 knots before the stall speed. Now, we let the airspeed stabilize at a stall speed plus approximately 5 knots. We must lower the nose and initiate a descent to maintain the speed. We will keep hearing the stall warning as we do this. We now know that we're flying at or very close to the angle of attack that gives us maximum lifting force. Therefore, any increase in pitch attitude should lead to an increase in descent rate. Let's try this out. Look at our vertical speed. As I slowly raise the nose further, we can immediately see an increase in descent rate. This is confirmation that we are now in the incipient stall. In this speed region, the controls will feel sluggish. Larger control deflections are necessary to generate movement without the axis. This is because of the low airflow speed over the control surfaces, leading to small aerodynamic reactions. In normal operation, we want to avoid stalls, but learning how to exit a stall is crucial for the day when we accidentally enter it. Our current airspeed is very close to the fully developed stall speed, which can be risky, especially near the ground. If we were to hear the stall warning sound in normal conditions, we'd execute a stall recovery procedure. Now, I want you to pay close attention, as this is a procedure you must master. It'll enable you to safely salvage an inadvertent stall in the future. The recovery works like this. The first thing I'm going to do is reduce our angle of attack. A slight pitch forward input to lower the nose just below the horizon is all that's necessary. This immediately takes me out of the stall by decreasing our angle of attack. As our airspeed is low, I smoothly but firmly add power all the way back to full. I meet with right rudder to stay coordinated and prevent the yaw. As airspeed climbs back up and reaches VY about 75 knots, I enter a climb to regain our lost altitude. As I reach my original altitude, I return to level flight.
As we've mentioned, increasing the angle of attack further in the incipient stall could result in a fully developed stall. Unlike in an incipient stall, a fully developed stall condition means that the airflow has separated completely from the wing surface. Before we explore the aircraft's behavior in the fully developed stall, we should consider a few things about the actual aerodynamic design of the Cessna. Airplanes, like the Cessna 172, have wings designed to make fully developed stalls less chaotic and more controllable. For example, the inner portion of the Cessna's wings are designed to stall before the outer portions of the wing. This allows the ailerons located on the outer wings to maintain effectiveness through the initial stages of the stall. It also means that in a stalled condition, a part of the wing is still producing lift, while another is not. This reduces the sharpness of the stall, and in practice, usually only a part of the Cessna wing is in a fully developed stall, while the other portions are in fact in the incipient stall condition. The stall characteristics of the Cessna means it is very difficult to enter an unstable or unsafe attitude. However, other planes may present less favorable stall behaviors, and it is important to know the stall characteristics of each plane that you fly. With all this in mind, let us now look at the Cessna behavior as it enters the fully developed stall. We must remember that the Cessna is a front-heavy aircraft. Recall from our previous lessons that the center of gravity sits about here. When lifting force is lost, we find that the Cessna desires to lower its nose. Therefore, as we enter the fully developed stall, we will first feel a force pushing the nose forward. If we allow the natural tendency to progress, our nose will actually lower as well. And note that this is a good thing, as a reduction in pitch attitude also leads to a lowered angle of attack on the wings, and most likely the end of the stall condition. This means that the stall behavior of the Cessna is self-correcting.
Let me show you how the Cessna behaves in a fully developed stall. Here we are in level flight again. We again prepare to stall by reducing the power to idle, while maintaining course towards our landmark. As speed begins to trail back, I maintain altitude. As we approach stall speed, we will this time maintain altitude until we feel the aircraft react with a nose down moment. This will be our cue that we fully entered the developed stall. There's the stall warning. I keep raising our nose. At this point, we can see that the Cessna is struggling to maintain pitch. If I keep adding pitch up inputs, we could feel the airplane being nose heavy and how it desires to reduce the pitch attitude. We have now stalled the aircraft fully. Let us recover. I allow the aircraft to naturally reduce pitch attitude. I smoothly add power to full, remembering our rudder. I maintain a stable attitude, regaining airspeed. As I reach 75 knots, I enter a climb towards our initial altitude. Note that the main difference between the recovery of an incipient stall and the fully developed stall is that in the fully developed stall, the Cessna tends to reduce pitch attitude by itself. We only have to allow the aircraft to lower the nose, at which point the recovery process becomes identical to the incipient stall condition.
The fully developed stall we've just seen was a straight stall, where both wings stalled uniformly. However, if we had stalled in a turn, or while flying somewhat uncoordinated, one wing may have stalled before the other, leading to a more complex reaction. Consider this aircraft in a turn. The outer wing is generating slightly more lift than the inner wing, and this is because it travels the longer distance around the turn. Traveling a longer distance means having a higher airspeed. So as we approach the stall speed, the inner wing, having the lower airspeed, will begin to stall first. Let us now consider the resulting motion of this unbalanced stall. Looking at the aircraft from behind, the reduced lift on the inner wing resulting from the stall will lead to a rolling motion. And this rolling motion will be in the direction of the inner wing. If the stall is allowed to continue to develop, we may end up with a very steep bank angle. And this steep angle may create a very rapid descent and a large increase in airspeed. The goal of the recovery is therefore to limit the airspeed increase and to recover a wings level climbing attitude. Because of this, we can say that if a large wing drop occurs in a stall, it is important to reduce the power to idle. This will prevent the airspeed from increasing too much. Once the stall has ceased and a sufficient airspeed has been regained, we will use coordinated aileron and rudder to return to a wings level attitude. And once the wings are leveled, we will slowly and carefully raise the nose to reach a climb attitude. As we do, we slowly increase the power back to full, transitioning to a climb at 75 knots.
Fully developed stalls with unbalanced stall progression across the wings are more pronounced from the cockpit. Safely executed, they're one of the most fun maneuvers that we can do in a small airplane. Let me show you how it's done safely. Let us consider the fully developed stall in a turn. Here we are, power off descent, flying at 68 knots. I will now enter a right turn. There we go. I'm stable at 30 degrees bank angle, and airspeed is stable at 68 knots. Now, I will raise our nose, slowly decreasing airspeed. As we approach our stalling angle of attack, we will hear the stall warning. Let's continue raising the nose. As the stall progresses, you can see the inner wing dropping. There we go, a rapid drop. Let's recover. Release aft pressure. Ensure power is at idle. Positive airspeed. I recover the wings level. Now I start raising our nose. Approaching the horizon, I'm going to add full power. Pitch for climb attitude. There we go. Coming back at my VY at 75 knots. We can now recover the lost altitude.
At this point, I'd like to discuss some of the real-life risks associated with stalls. First, I'll show you what can happen if ailerons are used while recovering from stalls. Here's a Cessna 172. Now, if this wing had stalled more than the other, it would drop. Sitting in the cockpit would feel this as a roll to the left, and our initial reaction would be then to roll wings back level again like this. And as you can see here, this causes the aileron on the stalled and the downgoing wing to deflect downwards. Looking at the wing from the side, we can see that such a deflection would cause the aileron to be directed further downwards. In effect, the downgoing aileron causes an increase of the angle of attack of this wing. If the wingtip is already stalled or close to stalling, the increasing angle of attack will further deepen the stall. This means that the very act of using the aileron may cause the airflow to separate and induce a strong stall at the wingtip. This would lead to what is known as aileron reversal. So let me explain. Consider this Cessna with the left wing more stalled than the right one. This would induce a roll to the left. Now remember, the pilot is trying to arrest a low wing situation by raising the wing, deflecting the aileron on the downgoing wing downwards. But since the wing stalls instead of providing more lift, a reverse reaction would actually occur. Instead of the aileron causing the wing to rise, the stall would instead lead to the wing dropping. In this video, you can see a pilot perform a stall exercise. The wing drops, but the pilot applies heavy aileron deflection in the opposite direction in an effort to counter the rolling motion. As you can see here, the wing does not raise, but keeps dropping. The instructor takes control and regains stable flight, primarily by reducing the nose attitude and breaking the stall condition. The student has just suffered from the aileron reversal effect. It's also important to remember that this course is for virtual flight simulation only, and some parts of the recovery training practice here is not transferable to real-life flying practice. For example, spatial disorientation can become a real threat in real-life operations as the balance system is exposed to unfamiliar accelerations, something that is not possible to simulate even in the most sophisticated aircraft simulators, such as full flight simulators used by airlines for advanced commercial training.
We've covered what happens when the Cessna flies too slow, so let us now move on to what happens in the high-speed segment. High-speed flight could result from mishandled spins. A spin is a rapid reduction of altitude in a low nose attitude, and all of the potential energy, which is our altitude, is quickly converted into kinetic energy, which means a higher airspeed. We could also intentionally enter high-speed descents to quickly reduce altitude. For example, if we are suffering from an engine fire. But high-speed flight is a non-standard flight condition that requires us to use a very careful approach. And I'll explain why we must take care not to overstress the aircraft. The Cessna structure is built with lightness in mind, because a light aircraft is an aircraft that is capable of holding more fuel, more people, and more cargo. Less weight also means improving the range and the performance of the plane. And as a matter of fact, most planes are built with relatively narrow safety margins to allow them to take off at all. Whereas in other industries, a safety factor of 3 or 4 may be used, most aviation structural strength components commonly use a safety factor of 1.5. This means that all aircraft structures must be able to withstand 150% of the force expected in normal operation before we can expect it to suffer deformation or failure. It is up to us as pilots, the professionals, to avoid putting any excess stress on the airframe. In high-speed flight, such as in a dive, the airstream velocity across the aircraft is high. This means we're experiencing strong aerodynamic reactions from all of our control surfaces. If we were to apply a full pitch-up input, we would create a very strong nose-up force. And this force would vastly exceed the safety margin designed by the manufacturer. It is very likely that the aircraft would suffer permanent and catastrophic damage. We must also consider the maximum approved airspeed in any operation, the so-called VNE. VNE stands for Velocity Never Exceed, and this is the absolute maximum airspeed of the aircraft. On the Cessna, VNE is exactly 163 knots, and it must never be exceeded. As we practice high-speed flight, we will dive close to VNE, aiming for an airspeed of about 155 knots. Jason will now explain how this is done from within the aircraft.
First of all, the Cessna is not a race car. Even at full power, the Cessna's top speed in level flight sits at around 125 knots. This is about 40 knots shy of the maximum speed. So in order for us to reach the target of just below VNE of 163 knots, we must dive. Let me show you how this is done in the airplane. Let's begin by ensuring we have plenty of altitude to work with. 7,500 feet is a good target here. As I prepare to enter our dive, I will reduce my power to about 1,500 RPM. This provides a safety margin to propeller overspeed, as the high airflow in the descent will push a propeller spinner faster. We also avoid using idle power. This way, we can reduce power if we find ourselves approaching VNE too fast. All right, let's dive. We put the nose attitude at about 15 degrees nose down. I use some trim to maintain this pitch. Watch the airspeed indicator closely. We can see the airspeed is increasing rapidly here. As airspeed increases, I find myself pushing on the control device. The increasing airflow is causing an ever-increasing pitch-up tendency due to the increased effectiveness on the stabilizer. I trim to remove some of the required pitch force. We are approaching VNE. Note the bottom of the barber pole area that marks VNE. Let's target about 155 knots. And make sure to use pitch carefully to stabilize the airspeed. At this airspeed, we must be careful not to overstress the aircraft. Any pitch or roll or yaw inputs must be small and delicate. Nudges are often enough to cause large reactions. Monitor RPM and do not increase power, as this could cause the propeller to overspeed. Let us recover. First, I gently and very carefully pull the throttle to idle. As I do, I also begin a very careful pitch-up movement. Small pitch control inputs are very important not to overstress the airframe. We raise the nose to climb attitude. I check our airspeed. If it's close to 100 knots or less, as here, I can slowly add full power again. From here, we can recover the lost altitude.
I'm sure you're eager to try this out for yourself. And you can right now inside Microsoft Flight Simulator. Just go to the Navigraph Academy website, and there you'll find all of our training content as well as our own in-game training sessions, allowing you to jump straight into the cockpit and start stalling. Also, please consider subscribing to our channel so that you can access all of our future training content. Also, by subscribing, you will be supporting our aviation training content right here on YouTube. See you up there.